Hello everyone, I would like to welcome you here today. My name is Nattida Juewong. I'm going to talk to you about visual simulation for detection of gray mold with biosensor technology in greenhouse. This presentation is part of the 13th International Conference on Information Technology and Electrical Engineering. My talk will be in 4 parts. I'll begin by looking at introduction. Then I move on to material methods and theories, keep on about result and discussion. Toward the end, I've talked about conclusion. I'm going to start with introduction. Lettuce is an annual plant of the aster family, Asteraceae. It's a plant that is native to Asia and Europe. Lettuce vary in shape and color, and the head can be loose or hard depending on the species. Some varieties may have thick and stiff leaves, while others have softer leaves. Leaf color can range from pale green to dark green, reddish brown, red, and brown. Lettuce is regularly consumed fresh. Nowadays, people are starting to pay more attention to themselves and are concerned about pesticide or other chemical residue in their food. Growing a chemical-free lettuce is definitely in favor of this food trend. Nevertheless, eliminating chemicals also means allowing vegetables to be plagued by numerous diseases. Gray mold is a fungus that is considered as major damaging disease in lettuce. Under humid conditions, gray fungi like mycelium and spore turn brown or tan. It can grow on young leaves and deep in the head of lettuce. The early symptoms of the disease sometimes go unnoticed, because they often occur in dense leaf shoots. Both species can be diagnosed in several ways: identified and classified by plate culturing and histopathological methods for traditional methods. Immunoassay-based diagnostic or molecular-based diagnostic, like enzyme-linked immunosorbent assay (ELISA). For modern farming, biosensors are currently the most advanced technique to enhance a rapid, specific, and sensitive pathogen diagnostic. The main objective of this study is to design and apply visual simulation to help to determine the optimal location of the biosensor for detection of gray mold in greenhouse. More specific objectives are to study an aerosol particle using flow simulation technique, to determine an optimal condition for biosensor installation based on the configuration of the greenhouse, and to study the efficiency of biosensor installation in greenhouse. I finished the first part and moving to the next one. Then, in the second part, material method and theory, I would like to outline computer-aided design, visual simulation software, and experimental procedure. Based on 3D design software, SolidWorks was developed in terms of computer-aided design program. Using this software, a biosensor for detection of gray mold was created in 3D model. The piezoelectric properties of a quartz crystal wafer were the basis for the development of novel sensors. The electrode of quartz crystal consists of gold plate and titanium adhesion layer. Electrode 5.1 mm diameter at hole on transparent surface 14 mm diameter. The electrode holder was made of ABS plastic that is resistant to chemical corrosion and will not rust. Copper wire of 1 mm diameter was used in electronic circuitry. Then this quartz crystal microbalance was installed in electrical enclosure with other components like Arduino Uno R3 mini breadboard and fan module using 5 volts of direct current. They were used for signal processing. Finally, biosensor device was placed in greenhouse. The greenhouse size was 4 by 6 meters. The installation of biosensor on an elevated lattice bed 5 meter range by 1.2 meter wide by 1 meter high with the 40 by 40 centimeter distance between planting plots. For this research, particle study in SolidWorks for simulation was tested to present behavior of airborne spore. According to solid solution, governing equation for sphere particles were force equation 1, drag equation 2, and Reynolds number equation 3. Governing equation and assumption were summarized in bottom left figure. An internal analysis investigates the flow through the structure. The flow simulation takes into account both laminar and turbulent flow type. The default settings were kept except for temperature and gravitational effect. Looking at the table, the outlet volume flow rate and environment pressure and the inlet volume flow rate were determined parameters and fast select. The objective of this virtual flow simulation was to study aerosol particle movement and efficiency of biosensor position. Limitation of this test study corresponds to the size of the greenhouse. The results were obtained by analyzing particles detected in biosensor in various scenarios. This simulation aimed to be a first step of determining the optimal position for biosensor installation. The position selected in this study was at one corner of the greenhouse. Green vegetable represent healthy lectures, where yellow vegetable indicate one infecting lectures on 12 different positions A to L on vegetable bed. Particle omnipresent in the greenhouse was shown on the simulation plot to determine the lowest and highest particle regions. Here is the new topic, result and discussion. As you can see on the screen, our subheading is viewing cut plot, flow trajectory, and particle study. Viewing cut plot select the top plane, which is on the z-axis with this default offset. After simulation, the velocity control were then displayed. The velocity was split into 10 color zones according to its value in meters per second. As you can see from the pictures, velocity control on z-axis for forecast of various positions of the door and two exhaust fans. The speed of air entered through the door decreased in scenario A and B. That the door was placed facing a vegetable bed, it is clear that the area of the high velocity in case D was greater than the other case, and the strongest airspeed is always at the fan, regardless of the position of the door and the fan. Flow trajectory was represented as a line with arrows, and it has the following parameter. This allows visual presentation of air path from the door to the fan. When the door was placed closer to the fan, the air flowed faster and circulated better as in case C and D. Some amount of air rises to the ceiling, then slowly travels toward the fan, whereas some flow directly to the fan position. Although the velocity in case D is great, the flow trajectory isn't consistent across all locations in the greenhouse. Based on velocity control and flow trajectory, case A seems to be the most suitable implementation for this study. So we use this case for the study of particles by testing multiple locations of the biosensor installation. For particle study, the spore device was created using solid user-defined filters. Particle property and trajectory parameters are presented at the top of the picture. The picture shows one example of particle detected on tree surface from an infected vegetable in position A. All simulations show the particles do not get a chance to pass through the surface parameter tree, as the other two surfaces have much stronger volume flow rate. However, the other two surfaces pick up different amounts of spore in different scenarios presented in the table. In most scenarios, the total particles detected from surface parameter 1 and 2 were close to 100 particles. In some scenarios, not all particles went through the fan due to gravity and air confined position in the area of infected vegetable. We try to move the position of biosensor to be placed in front of the exhaust fan, but particles cannot be detected on the device. Because the spore particles are small and light, they are carried over the biosensor's fan, the larger fan. So to summarize the main point of my talk, the simulation on SolidWorks made it possible to design a prototype greenhouse with real parameters. It also enhanced the study of detecting spores present in various positions by simulating air and particle trajectory. The result reflects that the location of the door, fan, and biosensor greatly affect the outcome of particle scattering. Indeed, the installation of biosensor should be placed where there is a good amount of air velocity. The air must also be circulated throughout the greenhouse at the time of exposing to the biosensor. The reason that the spores were not allowed to reach the sensor was due to the location of the sensor being too close to the exhaust fan. To eliminate the effect of both ventilation and exhaust fan, an additional chimney is recommended to install outside of greenhouse where the exhaust fans are located. Forcing the air to flow towards sensor device in the chimney before letting the air out This research helped in designing a more inclusive greenhouse prototype for future regarding biosensor installation tests and certain types of greenhouse in reality. That brings the presentation to the end. Thank you for your attention. It was a pleasure being here today. I will be happy to answer your questions now.